Hi everyone, this is the second video on differential equations of the first order. We'll be building on the work that we did in the first video, and the differential equations that we work with are going to be slightly harder, and so we need a new technique, a new method for solving them. You'll see that I've written a differential equation already onto the board, and immediately you should be able to see a difference between the type of differential equation that we looked at last time and the one that you have here. This one is dy by dx is equal to xy. And so rather than just being equal to a function of x, it's equal to both a function of x and y. And so we need this new idea of separation of variables to be able to solve this differential equation. We begin by taking the y over to the other side, so that we get 1 over y dy by dx is equal to x. Now we can integrate both sides with respect to x, and we get what the integral of 1 over y dy by dx is equal to the integral of x dx. The left-hand side reduces to the integral of 1 over y dy, and for the moment I'm leaving the right-hand side unchanged. And essentially we've got ourselves into a position now where we can integrate, and this is what we mean by the separation of variables. I'm just going to give you a summary of the technique. What we have to do is, first of all, we move x's to one side and y's to the other, very importantly either by multiplication or division, not involving addition or subtraction. It may seem a little unnatural at first, but we treat dy by dx like a fraction, and we split the various elements of that fraction so that we get one on one side with the y terms and the other on the other with the x terms, and then we integrate both sides. And that's really what we've done from this step to this step here. We wouldn't normally in your working expect to see the intermediate step, but we've moved the y from the right to the left, so we get the 1 over y. We've kept the x where it is, and then the dx on the left, the bottom of the fraction, moves over to the x that's on the right, and then we integrate both sides. But now we can integrate, and 1 over y dy integrates to ln y, and x integrates to x squared over 2, and then of course we need plus c. We can then write it as y is equal to a function of x by doing y is equal to e to the x squared over 2 plus c, where the x squared over 2 plus c is all in the power, is the exponent of the e term. From one point of view, of course, already we have now solved this differential equation, but it's often convenient to go a little further, and we will do that in this case, and reminding us of the rules of indices, we can split the right-hand side into e to the power of x squared over 2 times e to the power of c. E to the power of c is itself just a constant, and so we would more normally write this as a e x squared over 2. And there is our general solution of that differential equation. Now there's a reason for us going those extra few steps, and the a here you can see would be something of an initial term. If x is equal to 0, e to the x squared over 2 would become e to the power of 0, which is 1. So when x is 0, y is equal to a. And that is often important in these exponential relationships. In this second example, we've got another differential equation where we can separate the variables. Don't worry about the fact that we've got different variables involved, in this case t and x. Just treat them in exactly the same way. And we're going to begin by attempting to separate the variables and ending up with something that we can integrate on both sides. It would be a good idea for you to pause the video at this point and try yourself to see if you can follow the method of separation of variables. How did you get on? Well, we're going to be separating the variables, and it would make sense for the x terms all to go over to the left-hand side because the dx is in the numerator there, and therefore for the t terms all to go over to the right. So starting with the x, on the bottom on the right-hand side, it goes over and multiplies on the left-hand side. The dx is going to stay where it is. It's already there on the left-hand side. The cos squared t, we've got to move over to the right-hand side, and on that side it becomes 1 over cos squared t, and the dt, which is in the denominator on the left, goes over and is there on the right-hand side. So we've moved the x terms to one side, the t terms to another. We've treated the dx by dt as a fraction and split the elements of that, and the third step is to integrate both sides. But if we're going to integrate both sides, we need to do something to the right-hand side, and remembering that 1 over cos squared is equal to sec squared, we can then write that the integral of x dx is equal to the integral of sec squared t dt. And the integral of sec squared, that's a standard result, that's going to be equal to tan t plus c, and on the left hand side x integrates to x squared over 2. Now we need to find our value of c using the given value for x and t, so we can substitute those in. So when x is equal to 4, 4 squared over 2 is equal to the tan of pi over 4 plus c. Some of you will be thinking in terms of degrees, pi over 4 being 45 degrees, so tan of pi over 4 is 1. 4 squared divided by 2 is 8. Take away the 1 gives us that c is equal to 7. And so we can put all that now into our solution to give us x squared over 2 is equal to tan of t plus 7. We could of course go further, but I think for now we'll leave it at that stage. Our final example is a little harder, but nevertheless can still be solved by using this method of separating the variables. In this case, we're asked to give our final answer as y is equal to a function of x, and it'll be a general solution because we're not given any information that will enable us to find the value of c. So why not pause the video now and see if you can have a go at separating the variables for this differential equation. And by way of a hint, you may need to think about factorising the right-hand side first. How did you get on? If you began by factorising the right-hand side, you would have ended up with x dy by dx, and on the right you've got a common factor of y, and then inside the bracket 1 plus x. Well, now it's a bit more obvious that we can separate the variables. I can bring the y over from the right to the left-hand side to give me 1 over y, and of course I'm going to leave the dy where it is. I've already got on the right-hand side 1 plus x, and then I'm bringing over the other x on the left hand side and dx, and then I'm going to integrate both sides. Now you may have arrived at that point by your own work, but in order to integrate the right hand side we need to do just a little bit of additional work, and so we're going to be leaving the left hand side as it is, and then we're going to write 1 over x and the result of x over x, which is 1. Well, now we can integrate. So why don't you have a go at integrating this? Pause the video again for a moment or two and see how you get on. Hopefully you got something that looks like this. Ln of y is equal to ln x plus c, each term being integrated in turn and then the plus c at the end. But we can't leave it like this because we've got to have y is equal to a function of x. And so using what we know of logarithms, we can write y is equal to e to the power of ln x plus c, all of that being in the power of e. We're going to go just a little bit further than that, and we're going to split that right-hand side using what we know of powers. You might like again to stop the video and have a go for yourself. See if you can work out what it would look like once we do that. And if you've done that, you should have something like this. Y is equal to e to the ln x times e to the x times e to the power of c. You remember from the example we did before that e to the power of c, that last one there on the right, is itself a constant, and so we by tradition replace that with a capital A. E to the power of x, well, that is just e to the power of x, and e to the power of ln of x, and you can verify this for yourselves, simplifies to x. And so our final solution is y is equal to ax e to the power of x.